Let's start with a function x squared. If I differentiate this function with respect to x, I obtain 2x. Now this chapter we are learning the reverse of differentiation, going back to x squared from 2x. And this process is called integration. And whether or not it's indefinite or definite, we'll get back to this later. And the notation would be like this. What this notation is saying is that we're going to integrate this function with respect to x. Now think about this. If I change this to x squared plus 3, I will still end up with the same derivative, right? And as a matter of fact, as long as this is still a constant, I will still always end up with 2x. And so in general, whenever we do an integration on a function, we will always add a constant at the end. And we call that the constant of integration. And so while 2x is called the derivative of x squared plus c, x squared plus c is actually called the primitive function of 2x. So now, how do we actually integrate these? I would actually suggest you to always think of the reverse, the differentiation. For example, differentiating what would give just a constant 3000x, right? So look at this. Whenever we're integrating a constant k, all we need to do is just adding an x after that, and then a integration constant. So this would be the answer. So what about this one, integrating x to the 18th power? Since the x is on the base, okay, it would be some sort of power rule if we're doing differentiation, right? So whenever I'm differentiating x to the power of n, the n would go to the front and the power would become 1 less, right? So if I want the result to be 18th power, it would look like this, right? But I want 1 instead of 19 here. So then in the beginning, I need to have this over 19 to balance it out. So in other words, according to this law, it would become 1 over 18 plus 1 times x to the power of 18 plus 1 and plus the integration constant, which gives this. This actually still applies when the x is still on the base, but this time as a fraction as index. You just need to do the same thing on whatever the index is, which is 1 over the index plus 1 times x to the same index plus 1. And after simplification, we got this as our final answer. For this example, it's in terms of e now, but we can rewrite it into this form, which looks much prettier, right? Now considering differentiating e to the power of kx, the derivative would just be rewriting the same thing times this constant. Now if I just want the coefficient to be 1, then I will have the 1 over k to balance it out, to cancel out. So if we continue on our question here, it would be rewriting the primitive here times 1 over whatever this coefficient is, which gives this final answer. What about this one? You could actually break it up into 3 terms like that. But don't forget to put the dx, because these two things, the integral and the dx, would always come together. And so it leads to this. Now if we look at the last term, this is just a constant, 15 times 1 over x, right? And we know that the derivative of ln of x actually equals to 1 over x. But if you look at this integral of 1 over x dx, it's not just ln of x, but it's actually ln of the absolute value of x. So what this is doing is actually making whatever inside the positive. So for example, absolute value of negative 2 is positive 2, absolute value of negative square root of 2 is positive 2, and absolute value of positive 2 is still positive 2. But why do we need this? Well, if you still remember the graph of ln of x, you see that the domain of ln of x has to be greater than 0. This is a condition in order for this to be differentiable. And so therefore, when we integrate, your result has to be with an absolute value here. And so we apply the ln here and apply what we've just learned for the power rules here, and that would give us this answer.